geology, and atmospheric chemistry. The architecture of the Neumayer 3 station has been adapted to the environmental conditions of the Antarctic. It's built on stilts to keep it free of snowdrifts. Up to 60 scientists stay here in the Antarctic summer between November and February. Aerospace engineer Paul Zabe is the only member of his team who will also spend the winter here. His task is to grow fresh vegetables as part of the Eden ISS project.
The idea is to try out all of the necessary technology and operational procedures here in the Antarctic so that in future a greenhouse can also work in space. We're growing between 15 and 20 different species of plant. As a highlight, we also have little strawberry plants. We hope we can get them to flower so we can harvest strawberries in a few months.
Until the mobile greenhouse reaches the Antarctic by ship, the team has to take good care of the delicate strawberry plants. Inside the station, Daniel Schubert and Konrad Zeidler have tried to create the most ideal conditions.
Strawberries are difficult to cultivate, and that's why we've improvised and built our own little makeshift greenhouse. Of course, it's not optimal, but we don't have much of an alternative if we want to keep the strawberry plants alive.
It will take at least a few more days for the greenhouse to arrive. Then the experiment here can really get going. And soon, on the moon? In order to live and work on the moon for a longer period of time, worldwide research has to consider the conditions there and the differences to planet Earth. "71% of the Earth is covered in water. It has an atmosphere, a layer of air and gases that surround it and protect it, for example, from meteorite impact and damage from various types of radiation. It also ensures that temperature swings are moderate. 400,000 kilometers away, things look rather different on the moon. Water would have to be extracted from lunar sand by evaporating and condensing it. The moon has no atmosphere to protect it from the impact of any flying objects. It is also exposed to dangerous cosmic radiation. Temperatures rise and fall so dramatically that humans could not easily survive. To make that possible in the future, international students of the European Space Agency are conducting research with various experiments at the European Training Center for Astronauts in Cologne. Dr. Aidan Cowley is in charge of the spaceship EAC project. Outside the center, a lunar station will be built for test and research purposes.
So what you're looking at is a foundation at the moment, but in the next few months this is going to rapidly change into a building. We're going to have a large 34-meter diameter dome. We're going to have 700 tons of regolith simulant. Regolith is the name of the material you find on the lunar surface.
A small settlement, for now in Cologne, but in the not-too-distant future, one on the moon too. This is how the scientists imagine it will look. Inside, there's an airlock and a technical area. The main room is provided with daylight. Like in the ISS, the oxygen supply is provided by chemically based air preparation.
Another good example of why we should go back to the moon would be to understand the radiation environment. So if you're in low Earth orbit at the moment, you have the magnetosphere of Earth protecting you to a certain degree. But the minute you move beyond this, you go to the lunar environment, you no longer have that protection. And now you've got an entirely new radiation environment that will have a different effect on humans.
The lunar habitat will protect humans from this radiation with a strong outer layer.
This is the protective layer that we want to build. So the idea is that we take the material that is already on the moon, and by applying the microwaves, we could put it around the lunar habitat and build like a solid structure that will protect the lunar habitat from the meteoroids, the radiations, and so on.
Student Oriane Garcia from France is producing the heat required to sinter the powdery regolith, baking it into a hard layer. At the moment, however, it looks more like pebbles than a flat surface. On the moon, special robot vehicles would spread the lunar sand and sinter it at the same time, which would take about 3 months. Back then, the Apollo astronauts didn't have such a protective building.
Well, in 3 days, it wasn't bad. You could survive with just the regular protection that we had.
It took about 40 years for the scientists to figure out what the Apollo missions really brought back. It takes that long. You have to develop the instruments to be sensitive enough to learn what these stones, 300 kilos, almost 400 kilos of stones that have been brought back from the moon, what they really tell us.
As you come around there, there's a rock in the near field on this rim that has some white on the top of it. We'd like you to pick it up as a grab sample.
The 12 Apollo astronauts were not allowed to keep any souvenirs. The original lunar regolith was simply too valuable. Just a stone's throw away from the research center in Cologne is the DLR's Institute for Solar Research. Here, too, scientists are researching regolith radiation protection. Professor Matthias Spall and his team seek the most moon-like conditions possible.
What's available in abundance on the moon is moon dust and plenty of radiation from the sun. We would need several meters of moon rock or moon dust as protection from radiation from the sun and other cosmic sources. And that's one of the things that we're researching.
The experiment is called regolite, a word coined to combine regolith and light. Of course, it doesn't use real lunar regolith, but a simulant which has similar properties, and will be sintered to an entire brick using layered 3D printing.
What we want to show is that we can really produce a 3D object, whether X, Y, or Z, in a vacuum. And this is the technology we're developing here.
There's a vacuum on the surface of the moon. To simulate this, Miranda Fateri and Alexandre Meurice from France are creating the experiment in a vacuum chamber.
Our objective is to see what the mechanical properties are if we sinter something in a vacuum. If something better comes out, can we construct a better building with it or not?
The strong xenon beams imitate the sun and can create a constant heat of around 1,100 degrees Celsius. Channeled into one ray, they hit the 3 levels of moving moon sand below. It can take up to 5 hours under lunar conditions to bake a 3-dimensional object such as a brick.
We want to see whether anything comes out under the vacuum, and then do the chemical analysis. But the chamber is too small and very hot. When we have a bigger chamber, we can build a better cooling system and bigger components.
Scientists have to find the right parameters so that in future, today's result will look like the brick sintered without a vacuum. As a last step, they have to replace the artificial light with their solar furnace, which consists of 159 square mirrors and concentrates the light energy. It produces the necessary heat through constant sun radiation as exists on the moon.
You have to make use of every resource you have. And so I think 3D printing structures for habitations, all these things that we can do now with the existing infrastructure, existing materials on the surface will be something we'll want to take advantage of.
Back to the Antarctic. The conditions can change unpredictably. With the possibility of wind speeds of up to 60 knots, that's hurricane force. The weather here is the deciding factor. It's exactly the right testing ground for the scientists, with the perfect conditions for their research.
The Antarctic is the most remote continent of the world. It's not easy to reach. The people living here are dependent on the technology which keeps them alive, just like in a space mission. So it's the best place to test the whole operation of the greenhouse.
Almost everything is prepared for their Project Eden ISS, where they're planning to grow vegetables and strawberries in a mobile greenhouse. This platform has been standing here for a while, 400 meters away from the German research station Neumayer 3. The mobile greenhouse should have arrived here days ago, but the cargo boat transporting it to the site is making slow headway through the thick pack ice. 14,000 kilometers away in Germany, moon research is also being carried out. Various experiments for the project spaceship EAC are being carried out at the European Astronaut Training Center in Cologne. Belgian student Sander Koene is working on a virtual environment where future visitors to the moon can train.
With a simulation like this, we can train them into virtual reality as if they were already on the lunar base, and then have them interact with a digital rack and completely be able to do the experiment beforehand, instead of just being in a training room with a rack in front of you.
The virtual moonscape is still in the development phase. At some point, however, it could help with the preparation of future missions. A few rooms away, colleague Michael Regidor is busy working with different devices. His specialist area is 3D printing.
This is a 3D printer. It works with polymer, and the polymer is sticky behind, and basically it warms it up in here, and then it melts. And when it melts, you can put it over a surface. It gets cold, so it gets stick to the bed, and you can print lane by lane and then layer by layer and make a 3D object.
Heating, melting, printing. But for the next step, Michele is particularly interested in the reusability of the plastic.
What we are doing is here check if the materials work properly in the moon, and afterwards basically we will check with our piece if we crash it, and then we re-extrude it with this machine again and print it again if it works the same as the object before.
The coil containing the plastic would of course have to be much larger when it is transported to the moon. But once it's there, the plastic could always be reused. In Bordeaux, France, the 3D printing process is being researched in a parabolic flight. Professor Jens Günster from BAM in Berlin, the German Federal Materials Testing Institute, has developed equipment with his team to enable parts such as tools to be made from metal powder in zero gravity.
The aim of the experiment is to try out a new process of sucking in powder and then trying to fix it in a zero-gravity environment. So in principle, you can produce parts on demand. The part which has been sintered with the laser onto this plate should be able to be taken out and is ready for use.
Before each flight, the scientists draw their conclusions from the previous flight, making minor adjustments to try and improve the results of their experiment.
This is our third flight day. Last time we switched the material, and this time we have adjusted the parameters of the equipment to be able to apply the layer of powder. I'd say we managed to get about 70% of the powder onto the layer, and the rest flies away. We need to improve that. We can't have the powder flying around.
The Berlin research team is just one of many. In total, the participants here in Bordeaux fly for 4 hours on each of 3 days. There are 31 parabolas per flight. The aircraft rises steeply upwards from its horizontal position, reduces the thrust of the turbines, and flies for around 22 seconds at zero gravity. That is a particular challenge for the scientists, as the gravitational force during a parabolic flight varies. They've adapted the structure of their experiment accordingly. The experimental apparatus looks like this. The metal powder is in a container at the beginning of the parabolic flight. From there, it's spread in a layer over the base plate. So that it doesn't fly away in zero gravity, it's sucked in by gas from below and kept on the base plate, also during zero gravity. Then a laser melts the relevant information onto the freshly applied powder. It melts the loose metal powder into a compact structure. This is done with every layer, producing a three-dimensional object, in this case, a spanner. Günster and his team can follow this process, which is repeated several times via the installed webcams. The final results can be seen a little later in the laboratory. The metal powder has really been transformed into two small spanners. The experiment by Günster's research group was a success. In the not-too-distant future, all tools could be produced this way in space. In the Antarctic, the long wait is over. The cargo ship, the Agulhas II from South Africa, has managed to break through the ice and the unloading can finally take place. After a 10-day delay, the German scientists watch their mobile greenhouse being unloaded from the ship. Unloading on the ice has its hazards.
Plug our devices into sockets. We have to consider what kind of resources are available for producing energy. There are no rivers, there's no wind on the moon, there's no atmosphere. What is available is sunlight, and it's better than on Earth because it is not weakened by the atmosphere.
Jürgen Schleppi wants to produce mirrors to create energy. His experiment is also about how to use lunar regolith.
We'll have the materials we've brought with us, and there's this basaltic sand. What we can build out of basaltic sand is relatively simple bricks or walls by heating the material or baking. We can go one step further and produce basaltic glass from the material.
Schleppi uses an ordinary microwave oven to make glass from the moon sand simulant. He grinds the molten regolith, which is turned into glass, as smoothly as possible. The glass brick still needs a reflective surface. This is made in the final and most complicated part of the mirror production process. On the moon, there is an endless vacuum, but here it has to be created artificially. Schleppi fixes the glass elements which have been produced in recent weeks onto the frame of the vacuum chamber. Before he seals it, he adds one small piece of aluminum, which is heated and then evaporates, distributing millions of tiny particles.
The glass is different, but the aluminum is the same type we use for normal mirrors. It's looking pretty good now. It's not transparent anymore. So we can slowly turn off the system.
The aluminum, which was heated in the vacuum, is not only supposed to coat the inside of the vacuum chamber's glass dome, it is primarily meant to coat the experimental glass stones.
Good. It looks the mirrors have turned out really well. The mirrors have turned out really well. They should be able to reflect our artificial sunlight well.
That's what matters at the end of his experiment. It will only be a success if the mirrors made of moon sand can also harness energy from light. To test it, the researcher has built his own construction. His homemade mirrors have to pass the comparison test.
So here we have a reference. Which reflects sunlight, which reflects the artificial light. Rather the artificial light from this surface to the lens. From this surface to the lens, solar cell attached to a solar cell. The lens concentrates the light onto the solar cell, and then we can produce electricity. And then we can produce electricity. Measure at a certain voltage. We can measure at a certain voltage. We can read it here on the meter. We can read it here on the meter. With the reference surface mirror, we expect to produce about 2 volts.
2 Volt. 2 Volt.
Lights out. Lights out. 2.46 volts. 2.46 volts. It's working. That looks good. It's working.
2.46 volts are produced with an ordinary mirror surface. This is a reference level for the mirror made of the imitation lunar sand.
We're going to find out now whether it'll work in the way we imagine. 2.23 volts. 2.23 volts. That's We're only losing about 10%. We're only losing about the reference mirror compared to the reference mirror. That's really good for the. That's really good for the
solar cell, which would be positioned on the side of the moon that we always see from Earth. This phenomenon arises due to so-called synchronous rotation. The moon needs exactly the same time to orbit the Earth as it does to rotate on its own axis, almost 28 days. Since it rotates on its own axis, this means that the side with the solar cell faces the sun for 14 days. During this period, the energy production by the solar cell is constantly stable. For the other 2 weeks, the solar cell is on the shadow side. Solar energy cannot be produced during the long lunar nights.
And that night, it's cold.